So first of all, like, can you introduce yourself for the audience?
Yep, no problem. I'm Paul Comfort. I'm a professor in strength and conditioning based at the University of Salford in the UK.
Cool. I know since that last time we talked, you got invited to the TED Talk, right?
Yes, that's correct.
How's that? How's that?
It was very, very interesting. So it was a TEDx talk. So it's the shorter version of the full TED Talks. So 15 minutes. Um, and yeah, it was very interesting. You go through a sort of rehearsal process first. You get lots of feedback, and then turn up on the day with a live audience sat in front of you. No real prompts or anything, and also however many people are online, and then knowing it's going to be left online for everyone to watch afterwards. So it was very interesting. It was a really interesting day as a whole. Presenting was great. It was a real buzz. But actually staying around for the talks before mine and the ones afterwards, really, really interesting because it was so varied and people with some fantastic experiences. So yeah, it was a great day. Bit nervous, beforehand, but it was good.
I think you probably is the first strength coach being able to talk on the TED Talk, right? Am I right?
I don't know actually. I've not really looked into it, but possibly,
It's
possibly.
cool. It's cool.
Yeah.
Congrats, man.
Thank you. Yeah, no, it was a real privilege to be asked to do it, and like I said, a very very interesting day, and good fun to do. It's nice to get that information out to a different audience as well.
Cool. So today I kind of want to focus on your article about like isometric mid-dipole and
Yeah.
the data you're gonna look into, how you're gonna perform it, and like what is dynamic strength index, okay? So first of all, like how exactly are you gonna perform an isometric mid-type pole?
Okay. So ideal situation, you need a force plate or two force plates, depending on the system you have access to. To be honest, one would be completely fine. I don't think you really need to look at asymmetries necessarily in the isometric mid-thigh pull unless the athlete is injured. So force plate, you need a solid rig or a setup on a power rack where you can attach ideally a cold rolled steel bar so it doesn't flex. If you use a weightlifting bar, it really does flex and joint angles change. So you need to get the athletes get the equipment set up, and the bar needs to be positioned at a height where the athlete adopts the start of the second pull. So it's referred to as a mid-thigh pull, but actually, if you look at people's anthropometrics, sometimes it's higher than mid-thigh, sometimes it's closer to the crease of the hip if they've got a long torso and short arms. So the key thing is not necessarily making sure the bar is the middle of the thigh in terms of anatomically, but making sure that they're in a dorsiflex position, trunk is upright with no more than a 5 or 10 degree forward lean, and that should replicate the posture you have for the second pull. Normally with the clean, because it's the clean grip, but actually in terms of your body posture, we ignore the bar for a moment. It's the same position, it's that power position for a snatch or a clean, and that's really really important to get that position correct. It's the position where we can generate the highest forces and the highest rates of force development, both ballistically and isometrically. And it's the most reliable posture to be in as well. If you use a different posture, you will end up with lower forces. So it's very, very important. And then if we're monitoring the athlete longitudinally over time, that's even more important because if we had a more flexed posture, and then we go to that ideal posture, you will get an increase in performance. But it's not because you've trained them and they've adapted. It's just because you change posture. So that posture needs to be very carefully adopted. Ideally, measure their joint angles while they're in that posture and replicate those joint angles the next time. And plus or minus 5 degrees is generally okay for the knee and the hip. And that might vary slightly depending on any changes in range of motion. And we're not that accurate at measuring with a manual goniometer. So, plus or minus 5 degrees should be fine within that. And then the other thing to do is make sure we use an overhand grip, so the clean grip you would normally use, and use lifting straps. If you have time, some athletic tape just to make sure that they don't lose their grip, but definitely use lifting straps. I've seen so many images online of people not using straps, trying to use an opposing grip. And I've got some pilot data that shows you generate at least 10% less force using an opposing grip. Dramatically less force if it's an overhand grip without straps. And that does depend obviously on the individual's grip strength, but we want to avoid it being an assessment of grip strength. It's an assessment of lower body force production. And if we don't use straps, the rate of force development or force at early time points is dramatically lower because people are more cautious with applying force if they think their grip may not hold up.
So since there's a consideration about like the gripping strength, why use like isometric mid-high pull instead of like pushing quarter squat iso?
Yeah, you can definitely use that. You can definitely use an isometric squat, and a few researchers, and I know quite a few practitioners that use that. Personally, I find that when we test different athletes or test them using both to see which is better, most of them actually prefer the isometric mid-thigh pull because it doesn't have that compression into the trapezius. You're still loading the spine in the same way. The same amount of load will still go through the spine, but you don't have that perception of compression because you're not pushing into something immovable above you. You do end up with slightly higher forces most of the time with the isometric mid-thigh pull. However, again, I've seen individually, some people produce slightly more with the isometric mid-thigh pull than the isometric squat, purely because it's uncomfortable. And if we're after rapid force production, we can't put any form of pad on the bar to make it more comfortable on the trapezius, because that pad will compress, joint angles will change, and rate of force development or force at early time points is then compromised. Yeah, so we generally go with the isometric mid-thigh pull because most of the athletes that we test and work with actually prefer doing that test.
Right.
There are some individuals, some rugby teams I'm aware of where they regularly use the isometric squat instead. But if you think about the physique of most rugby players, they've got very well developed upper bodies and trapezius, so you don't have that same level of compression and discomfort. And most of them won't complain if it's uncomfortable either. Whereas I find working with soccer players, they would all complain if it's uncomfortable.
Yeah. So I know we've discussed this before and you talk this topic on different podcasts, but still, besides isometric mid-thigh pull, is there other like tests you're gonna do in your like battery of tests when you assess like athletes' physical performance?
Yeah, well, if we're focusing on sort of the use of force plates for the types of testing, most of the squads that we go and assist and do some testing and screening with won't necessarily have force plates, or will only have one set. So we'll turn up with 3, 4, 5 sets of force plates and get through the testing really quickly. They might also do some aerobic testing, sprint, change of direction, etc. And that's something they generally standardize. But the testing we then end up doing with them with the force plates will be a counter movement jump and some type of rebound jump. So the counter movement jump, cueing them to jump is fast and high as possible. Because what we don't want is occasionally you get some people who will almost do a full depth squat, because in that situation, you give yourself more time to apply force for a bigger range of motion. And if you're conditioned to do that, you get a much higher jump height. But that's not how people normally jump. I don't think, apart from on the odd occasion in watching volleyball where people have the time to squat deep, I don't think in most sports you ever see somebody jumping that way. So we're after rapid force production using the stretch shortening cycle, so a counter movement jump, and then normally hands on hips, so we know it is just lower body and we don't have that additional contribution of increasing forces with the arm swing on the way down and greater acceleration on the way up from coordinated arm swing. And then we normally do some type of rebound jump, and at the moment we're looking at a few different options. So we've been collecting data where we can with a standard drop jump, a counter movement rebound jump, and the 10-5 rebound jump test. They've all got limitations, which is why we're trying to assess all of them, identify the differences between them and the limitations, see if we can work around some of those limitations, and identify which may be best for benchmarking, but also for longitudinal assessment. So with something like the drop jump, you don't drop from the height of the box. Nobody drops from the height of the box. people will generally step down and lower their center of mass. And therefore, all of the calculations we have afterwards, if we're integrating the false time data, are flawed because it's making the assumption that you've fallen from, let's say, 30 centimeters. But if you look at the research in this area, and there's stuff going back over 20 years by Kabili, Bobbitt, and there's also some more recent work by Lisa Costley, who's based in Ireland, which shows that there's at least a 20% variation from the box height. So they could be 20% lower, they could be 20% higher in terms of the height they fall from. And that can vary between repetitions and between sessions, which is a real problem, because then we're not comparing like with like for that individual. And if we assess across a squad of athletes, we're also not comparing everyone dropping from 30 centimeters. It could be 24 centimeters, it could be 36 centimeters, or even more varied than that. So we try and standardize that as much as possible. But as I said, there are some limitations. If there's a big change in their strategy, it's obvious. But 2 or 3 centimeter lowering of the center of mass or elevation of the center of mass, you can't always observe that. If you then look at something like a counter movement rebound jump, people are pretty consistent with a counter movement jump that they do preceding the rebound jump. So with that, we're trying to see if that's a more reliable or more consistent task. However, the problem is if we then look at that with youth athletes who are developmental, we might see big improvements in their counter movement jump performance across a season. So if at the start of the season they had a 30 centimeter counter movement jump, at the end they've got a 40 centimeter counter movement jump. That's fantastic. They've improved. But if then we're assessing the rebound jump that follows that preceding counter movement, we're no longer comparing like with like. So there's more work that needs to be done there. And that's the same principle then with something like the 10-5 test. If an athlete is very fatigued or is better at jumping because they've improved, they've adapted, we'll see either a decrease or generally with the developmental athletes, a progressive increase in their jump height, which means that they're falling from a higher height, which makes the jump more demanding. So we might actually see, if they've improved their jump performance, we might actually see a decrease in reactive strength index because there's a more demanding task. Yes, we have an increase in jump height, but we may have a disproportionate increase in contact time because it's so demanding. And that's important because then we actually need to make sure that we look at the components of reactive strength index M. We can't just look at the reactive strength index itself. We have to look at the jump height and the time. The problem is most athletes and coaches want one number, but we can't just give them the one number. We have to then, break that down and identify if it has changed, why did it change? Because if RSI has dropped very slightly, but my athlete's got a 30% increase in jump height, I'm pretty happy. As long as they're staying below 250 millisecond contact time for the rebound, that's pretty good.
Love it, love it. People always talk about like reactive strength index. They only see the number, but you kind of like explain it to us, like how can we like look into the number, not just like reactive strength index. Love that.
Yeah. And that's also
And
really important when you look at people that understand the test. Some athletes are very, very clever. So they will intentionally minimize contact time and get it as short as possible. And that inflates reactive strength index, but it massively reduces their jump height, which then makes the subsequent jump easier because you're falling from a lower height. So you have to be very aware that athletes will sometimes adopt that strategy and cue them to, put in a maximal effort.
love that. Since you brought up like jump performance, I noticed that you cooperate with Chris Bishop, right? Am I right? About
Yeah.
the newest article about selecting the metric that matters.
Yes.
So kind of want to circle back to like isometric mid-type Like want to go to the jumping performance late a little bit later. So when it comes to like I isometric mid-type is there like certain metrics you're gonna like be looking to? 어떤데요? Hey man. 그래? Can't hear you. Can't hear you.
No idea what happened then.
No worries, man. No worries. So I was talking about like uh when we go back to like isometric mid typo, is there like certain metric you can look into?
Yeah, well, you definitely look at the peak force, and you should be ratio scaling that, so dividing it by body mass. And that's important because then if the athlete's body mass changes, we can identify if the change in force is because of a change in body mass or when it's relative. And we can also then compare that to other athletes who are bigger, smaller. We can compare across age groups, and then we can also compare males to females if we need to do that. So peak force, relative peak force, and then there's a really nice study completed by Professor Greg Half and some of his colleagues published in 2015, which identified that depending on how you evaluate rate of force development, it can be more or less reliable. Now that might sound strange because it's force divided by time, so surely there's only one way of calculating it, but you can calculate it based on the peak, the mean, and that mean can be from 0 to whatever time point you choose, 0 to 50, 0 to 100 milliseconds, or it could be 150 to 200 milliseconds, so that just that 50 millisecond window. And actually what they observed is that if you had a moving average window of 20 milliseconds, so let's say you're looking at rate of force development over 250 milliseconds, you look at the greatest change in force over 20 milliseconds within that 250 millisecond window. And that came as the most reliable. However, the biggest problem that we have is there's so many studies out there that don't clearly report, and I've probably done the same, don't clearly report exactly how that was calculated. Was the data smooth? Was a moving average window used? And the thing to bear in mind with this is if there's an increase in force at 100, 150, 250 milliseconds, if you look at a force trace from an isometric test, you just get a rapid increase. So it's a little bit different to dynamic tasks. So if there's an increase in force at 150 or 250 milliseconds, rate of force development has to be higher. And it's much more simplistic. We don't have to worry about how it's calculated. As long as the way we identify the onset of force production is the same, then force at each of those time points tells us that rate of force development has increased. So we now tend to use force at 150, 200, 250 milliseconds. With some athletes, we'll look at earlier time points, but unless they're very, very familiar with the task and they're used to performing heavy weightlifting type exercises, the earlier time points aren't always reliable. Now, one other thing that you can do with that is look at the percentage of force that they're actually, the percentage of the peak force that they can generate at each of those time points. Because if we're looking at adaptations to training, we need to know if force at 250 milliseconds increased, has that increased because they can now express force more efficiently, more effectively, or has that increased because actually they're much stronger now? And we need to identify that because if they've just become far more efficient at producing force and their peak force hasn't changed, that's great. But then we probably need to focus on maximum force development. So it's a really good way of identifying whether our previous block of training resulted in the adaptations we wanted to. So if we were focusing more on ballistic, plyometric, and lower load weightlifting exercises to enhance rapid force development, then we would expect to see the percentage of the peak force increase at certain time points. Whereas if we're focusing on maximum strength, we would expect to see peak force increase. And therefore, you may actually see a slight increase in the force at those time points, but purely as a product of the fact the athlete's got a lot stronger. And again, that can help us to then identify, do we need to really focus more on rapid force production or maximum force production? If an athlete's producing 80 or 90% of their peak force within 250 milliseconds, they're efficient. That's great. So we then need to make sure we increase that ceiling and get them much stronger.
So why shouldn't we be using like time under like 250 milliseconds?
normally looking at under 250 milliseconds because the propulsion phase of most tasks is less than 250 milliseconds. So if you look at the ground contact times with a lot of sporting actions, they are down below 250 milliseconds, apart from your initial couple of strides when you start to accelerate. And even if you look at somebody when they do a reactive jump, so they might do 2 or 3 steps and then take off, even with 1 foot. In that situation, there may be a longer contact time, but there's a braking phase followed by a propulsion phase. And the majority of the time, we're looking at the force at those early time points of 250 milliseconds or less. The more that time point increases, the closer you get to peak force. And what we really need is in sporting tasks is the ability to produce force as quickly as possible. So, like I said, 150, 200, 250 tend to be the most reliable value time points that you can get for some of these isometric tests. It's different if you look at single joint. So there's some fantastic research for single joint isometric testing, which has been done by Jonathan Follen's group, Per Agard's group, etc. There's a huge amount out there. You get much more reliable rapid force production and rate of force production if we're looking at a single joint. There's less things that can go wrong. There's less give in the system that you've set up. There's less give in terms of the number of joints being assessed. So it is slightly different if we're looking at a multi-joint test compared to a single joint test.
Love that. Love that. So that's things for like isometric mid-thigh-pull. So you mentioned like rebound, counter movement, jump, right? So when it comes to like counter movement jump and rebound counter movement jump, is there like besides reactive strength index, is there like or besides like jump height, is there like other metrics you're gonna look into?
Yeah, well, if we're looking, still considering the isometric mid-thigh pull, something like dynamic strength index is a good thing to assess as well. So that's how much of your what percentage basically of your isometric force can you produce during that ballistic task, during the counter movement jump. So you take a ratio of counter movement jump peak force divided by isometric mid-thigh pull peak force. And the recommendations are that if you score 0.8 or higher, that means you're producing at least 80% of your isometric peak force during that dynamic task. So you probably then need to focus more on increasing maximum force production. If the value is 0.6 or lower, you're only producing 60% or less of your isometric peak force during a dynamic task. And therefore, you probably need to focus more on your ability to produce force rapidly. Somewhere between 0.6 and 0.8, you can probably get away with a mixed methods approach. So you have a combination of heavy strength training and some more ballistic and plyometric type tasks. And it generally does show us what we would expect. So we collected over pre-season over 600 football players worth of data. And I would say over 95% of them were demonstrating really, really effective rapid force production. So during the counter movement jump, they were getting 80 to 90% of the maximum force production. But they weren't very strong. We were getting 25, 30 newtons per kilogram for most people. But they might have had 40 or 50 centimeter jump heights. So with that, we didn't even need to calculate dynamic strength index necessarily. If you've got a low relative peak force and a high jump height, we know they're efficient and effective at producing force during those tasks. They just can't produce a high force. So the simple thing they need to do is go away and actually maximize force production. But if you look at the training of most football or soccer players, there's a far more ballistic dynamic training on the pitch, in the gym, etc., than there is maximum strength. We generally see the reverse if we look at forwards in rugby, that most of them are very, very strong. They just need to be more efficient and effective at expressing force rapidly. So it generally does tell us what we expect to see. Now, again, because it's only a ratio, we still need to consider what their peak force is in both of those components. And if their isometric peak force is low, just get them stronger. And while you're getting them stronger, focus on the technique of some of the ballistic and plyometric training, improve their skill in those sorts of tasks, and then have less emphasis on the ballistic and plyometric and more emphasis on strength. And as I said, we're rarely surprised with what we find when we do these tests. When you're actually assessing them, you can tell if they are very good at expressing force rapidly.
So you mentioned a lot of time about like force production, and uh nowadays there's like coaches have like force plates. They're getting all these kind of data. So why exactly do we like have to like measure force production? Why is it so important for our athletes?
I suppose it's basic physics or biomechanics. What determines acceleration is the impulse that we apply to the ground or to an object if we're throwing it. So if we think about jumping, sprinting, etc., it's the amount of force we apply over a given time. So impulse being force times time. And we have limited time. As we've already discussed, there's limited time to apply force to the ground because of the contact times. And as you're running and you get faster and faster, the amount of time your foot's in contact with the ground to allow a propulsive force progressively decreases because of your horizontal velocity. So then it's really important to continue to accelerate or maintain speed that we have to produce very high forces in a very short duration. And it's not just the impulse, but it's relative impulse. So it's the impulse that we apply relative to our body mass. So if I have a coach telling me I need to get the athlete bigger and stronger, I have to get a disproportionate increase in the amount of force they can produce compared to the increase in mass. Otherwise, they would get slower. That being said, if they're heavier and moving at a similar speed, you've got greater momentum. So with sports like rugby and American football, you're going to be harder to stop. But ultimately, it's impulse that determines both acceleration and deceleration. So we've got to make sure our athletes have the ability to produce high forces over a short duration to give us the highest impulse that we can possibly achieve to then maximize their acceleration.
What if like some of the coaches don't have the access to force plates? What can they do?
Some of it's relatively simple. Just look at what their relative strength is with good technique with a squat, possibly a deadlift. Squat's probably a better indicator because it's easier to standardize posture, technique, etc. And if somebody's got a high relative squat performance and a low jump performance or a slow sprint time, then we can actually use that information to identify training priorities. So if you've got somebody, and again, if I use the example, and this is based off real data that we've collected, if we use an example of a rugby athlete, especially a forward, they might be able to squat well over double body weight. So 120 kilogram athlete is putting 250 kilograms on a barbell on their back and squatting. We might not even need to assess that because they might be doing that for sets of 3 or 5 repetitions in training. So I don't even need to go and do a 1 repetition maximum. I know that athlete's strong. But if their acceleration is poor with initial sprints or their jump height is really poor, that tells me they need to work more on their expression of rapid force or the technique with how they try and accelerate or how they jump. Most of the time, if it's a senior athlete, it's just expressing that force more rapidly. Because again, we don't want to decrease their body mass because that's really useful in a game of rugby. We can look at the reverse for soccer or football players that if they've got a really low back squat performance, but they've got really good vertical jump, fantastic sprints, if they're doing 5 meters in under a second, their acceleration is really good. But that's not going to improve any further if they're really, really weak because they're using the force that they can produce very efficiently. So, they're up at using a high percentage of that force. Now we need to increase that maximum force production to be able to improve that. If you have other technology available, if you have a strain gauge, you can do an isometric mid-thigh pull with a strain gauge. Most strain gauges you'll only get peak force from. The majority don't sample at high enough frequency to give you force at early time points. If you have, you can get apps on your smartphone to assess jump height, there are some limitations, but they're reliable. If we use the same method each time, they're reliable for calculating jump height. We won't get peak force from it, but we can actually quantify what their jump height truly is. Or if you have a jump map or an optoelectric device, we can assess jump height with that as well. most of the time you can see that, you can see which of your athletes are jumping high. You might not be able to quantify it appropriately, but it can still give you a good indication of, we've got an athlete who's strong but jumps high, sprints fast. Let's focus on force production, or the reverse. Right, we need to focus more on the ballistic aspects.
So if I want to like make my athlete to be able to like produce force more rapidly or like getting stronger, besides like let them like lift heavier, like squat heavier, like deadlift heavier, is there like other approach to it?
But for maximal strength, the most effective approach is, progressive overload using more resistance. But you also have to identify, if your athlete isn't particularly muscular and is very strong, what you might find is the majority of the adaptations could be architectural. So you've actually got some fiber packing. The fibers have moved to a more pennate angle, which actually increases the force production within that cross-sectional area. The tendons may be really, really stiff, so we actually get rapid force production. And the neurological system may be working really effectively. You may have optimized everything within the musculature they have. In that situation, we probably need a period of higher volume training. That could be typical hypertrophy training, or it could just be higher volume strength training, because we generally get more muscle mass. The primary stimulus is normally the volume of exercise rather than the intensity, which is why you can develop muscle mass with low loads and high repetitions, or high loads, relatively low repetitions, as long as it's a high volume. It's a bit more complex than that, but in general, if we increase the cross-sectional area of the muscles, we have basically a bigger engine to be able to produce those forces. It's a bit like if you have a car that you start modifying in every way you can to make it faster, but the engine's the same size. You get to a certain point when it will not go any faster. The only way we can make it faster is to put a bigger engine in there. So in that situation, with some athletes, you may have to focus on increasing muscle mass as well. And we do increase force production from doing weightlifting type exercises. They're not as high absolute load as what we get with normal strength training, with squats, deadlifts, front squats, split squats. And it doesn't just have to be a back squat. Any type of squatting pattern performed correctly will make you stronger with that extension of hip, knee, and depending on the movement you're doing, possibly the ankle as well. So we have to evaluate whether we need the athlete to increase muscle mass. So we've got that bigger engine, for want of a better phrase, and then we can focus more on optimizing force production. Now we've got a bigger muscle. And we can also use some of those sort of weightlifting type movements with high loads to increase force production, but also that helps with rapid force production. And then one of the other things we need to make sure the athletes do is move with intent, that they're not just going through the motions. They're aiming to move the bar or the weight as fast as possible with good technique. But what slows them down and decreases the velocity is purely the load that we've given them to lift.
So beside the second pole position, is there like certain position you're gonna train them to be stronger?
Yeah, in terms of training, all postures within weightlifting or weightlifting movements have a benefit. If we think about starting with a barbell on the floor, that takes a huge amount of postural strength to lift a heavy load from the floor to get to the knee. So that first pull in weightlifting, similar, not identical, but very similar to a deadlift movement. And that really helps with postural strength. Helps, strengthen the spinal erectors, the gluteal muscles, the knee extensors, etc. If we're doing the movements from the knee, so if we hinge down to the hip and add a counter movement, or if we start with the weight on block, so the bar's at the knee, we then stimulate the stretch shortening cycle because we have to go through that rapid transition phase. You can't lift quite as heavy a load as you can from the floor if you're good at lifting, if you're technically proficient. But that also forces you to produce force rapidly then, because if we've reduced the displacement and therefore the time to apply force, you really have to emphasize rapid force production. And then we can move up to, obviously, to that mid-thigh position, and then we've reduced that range of motion. Now, the interesting thing with changing range of motion with weightlifting exercises is we decrease training volume. So if you think about it, if you're trying to peak or taper for a competition, or just because you're going to go into a higher volume training phase next, if we've been doing cleans, starting at the floor, catching full depth, then you squat out of the bottom position, that's a lot of displacement of that barbell. And it's not just a clean, you actually squat back out of it. So there's a lot of work performed. If you then change that to a mid-thigh power clean, we've got a much reduced displacement during the propulsive phase. You catch in a shallow squat and then drop the bar back down onto blocks or however you're performing it and start again. So while we might be using the same load and doing the same repetitions and the same sets, if we've massively reduced displacement, we're now doing less work. So at certain times, especially close to competition, we can manipulate what the athletes are doing in their training sessions to reduce training volume, not just looking at the sets times reps times load, but also thinking about the total displacement we go through. And also, if you're only going through smaller ranges of motion, you're not going close to end range, you're less likely to induce muscle soreness as well. So, 2 days before competition, that could be an ideal stimulus to still stimulate the neurological system, but far less fatiguing than what you may have done 2 or 3 days prior to that.
Cool. So, kind of want to circle back to like you mentioned, you go through like 600 football players. Is that true? 600 football players data?
Yeah.
How exactly do you go through like 600 football players data?
With difficulty. Luckily, we've got a couple of PhD students that work within football, so that's made it a little bit easier to access those football teams. And also because we're working with so many different teams and we have access to force plates, if we can go below sort of the Premier League level, most of them don't have access to the equipment and are willing for you to go in, collect the data. Luckily, with the way we do it and the way that one of my colleagues, Dr. John McMahon, has set everything up, we can go off-site testing. He could be sat at home or in his office at work. And the data goes straight to a cloud-based system. He can then extract it from there. And by the time I've packed up all the equipment and I'm leaving the facility with my PhD students and other members of staff, he's probably already started sending the reports back to the strength coach or the sports scientist. So it's done that quickly, which is absolutely fantastic. So they then invite us back in because it's so quick. You think about it from the point of view of an applied practitioner, you don't have much time. You're pushed for time. So if somebody else can come and collect that data and then send you the report afterwards, it saves you hours or days potentially. So it's just made it much easier for us to go in, and we've tested it from sort of younger level academy squads, the under 9s, under 10s, right the way through to the first team. And we tested across multiple levels of competition as well. So yeah, it's been interesting because actually we're finding similar sorts of things to what you would expect, that in general with the football players, they need to get stronger.
So, like the barrier test, you just mentioned, you do like isometric mid-thigh pull, counter movement jump, rebound jump, and 10-5.
Yeah.
Is it gonna change when it comes to like training different athletes, like let's say rugby, basketball, soccer, sprinters? Is it gonna change?
Not really, because again, we're not looking at a sports-specific movement or task. We're looking at assessing maximum force production during a slow stretch shortening cycle task, so the counter movement jump, and force production during a fast stretch shortening cycle or rebound task. And all athletes need that. They all need to produce high forces, or we need to quantify how high a force they can produce. They need to be able to produce that in a reactive manner with a very short contact time or movement time. And they need to be able to produce it during slower stretch shortening cycle tasks. So we've just found that that's the three types of testing that give us a really comprehensive overview of what people need to do. And occasionally you might find that the ballistic capability in terms of the counter movement jump is great. Maximum force production is great, but it's just the reactive component that they're not particularly good at. Other times they're strong enough. It's all the ballistic and plyometric that they struggle with. With the football players, it is generally the strength aspect that's most limiting. Unless, the goalkeepers are generally pretty good. And we find the reverse with rugby players. Normally it is the more ballistic and explosive force production that they need greater emphasis on, because they do a lot of heavier strength training, partly because they have to be more muscular, they have to be heavier. So they naturally put on more muscle mass, and that helps to increase their maximum force production capability. So in reality, if you look at how some football players train, how some rugby players train, then if you look at rugby league instead of rugby union, where it's a faster paced and a greater distance they cover compared to rugby union, they all train slightly differently. And the types of training they do really then explain the force production characteristics that we observe. So yeah, we don't really change it dramatically based on the type of sport, because we're not assessing a sport specific task or skill. It's how effectively can they produce force in these different scenarios.
Cool. Love that. That's kind of like all the question I have for today. So if there's like coaches and therapists are interested in what we're talking about today, where can they reach out to you?
I'm on Twitter and Instagram, Paul Comfort 1975, so it gives away my age. Or they can email me. My email address is p.comfort@salford.ac.uk.
Appreciate that, man. Appreciate it.
No problem at all. It's been a pleasure.